The extended arm was another project where this is an 11 degree of freedom hand. Wrist rotation, thumb rotation, individual finger flexion, but each finger opens and closes. So each finger effectively is a gripper in itself. So an 11 degree of freedom arm. And in this performance, where I use this manipulator, my left arm is computer controlled. 15 to 50 volts of electricity are directed to different muscle sites. So my left arm is involuntarily moving for the whole 4 hours of the performance. So I'm extending my right arm to primate proportions, whilst my left arm is being sort of automated to perform continuously for 4 hours. And we also had streamed this live on the internet. So if you were watching this on the internet, you could see the streaming of the video, but also we had constructed a 3D model of the mechanism, and that kind of mimicked the movements of the performing hand. And this performance was performed in Avignon, and it was a 4-hour continuous performance. I'm working now with Brunel University on an ambidextrous arm. So imagine a universal human-like manipulator. The fingers bend one way, the thumb rotates, you've got a right hand. But the fingers can bend completely the other way, the thumb can rotate back. So you've got a right hand and a left hand, or a combination of both, all in the one system. So you don't have to construct a left-handed prosthesis or a right-handed prosthesis. You can just have one universal kind of prosthesis. And here we were sort of doing we're just beginning to program it, and you can see the ambidextrous nature of the fingers and the hand. And this is actuated by a bundle of pneumatic rubber muscles. So the hand is not a stiff mechanism, it's compliant, it's flexible, and that's the rubber muscles. 3 bar of air pressure, and the rubber muscle expands in girth, contracts 20% of its length, so it's a very strong linear actuator. Stepping back to an earlier project, this is a small operational machine that was designed for the inside of my body. If you can imagine your stomach empty, inflated with air, and when it's closed, this capsule sort of structure, it's a worm, screw and link mechanism, so it's a simple mechanism. It had to be because when it was inserted into the stomach, it opened and closed, extended and retracted, had a flashing light and a beeping sound. So you have to imagine this as a simple machine choreography inside a soft and wet part of the body. So the body itself, to me, is a kind of evolutionary architecture that is a structure but also full of empty spaces. So why not design an artwork for one of the empty spaces? The body becomes a host for a work of art. The body is not a site for the psyche, nor for social inscription, but it's a site for a sculpture. This is a clean image of the inside of my stomach. When we were doing these images, the endoscopist discovered I had a polyp growing in my stomach. So what began as an artistic experiment quickly deteriorated into a medical melodrama because we had to perform a biopsy there and then. Fortunately, it was benign. And this is a project that was begun about 4 or 5 years ago, but has not yet been realised. But what we're doing here is we are engineering a small robot. It's robust enough and reliable enough to be able to climb up my tongue and into my mouth. I just have to remember not to swallow. We are making a few extras just in case. But of course, this is sort of indicative of the increasing intimate connection between the human body and its future robots, which will not only be micro-miniaturized, but will be nano-sized. Nano-sized sensors, nano-sized robots. There's a nano chassis now that they've been able to adhere a bacteria to. The bacteria provides the propulsion for that nano-sized machine. So this is all plausible, and of course, medically, we do not have an early alert warning system when something pathological is happening at a cellular level. By the time you feel the lump in your breast, it's too late. Symptoms have surfaced. But if you could detect at a nano level the first beginnings of a cancerous cell, cluster of cells, then you could easily target them and kill the cancerous cells before they cause any damage. I've always been interested in insect and animal locomotion. And in this project, in 6 months, we built a 6-legged walking machine large enough to, this is only 3 meters in diameter. So 1, 2, 3 meters in diameter. So it pretty much fills all this space. I could stand on this machine, and there's an upper body exoskeleton, electromagnetic sensors on each segment of the upper body exoskeleton. By making different gestures, I could select the different walking movements. The robot could walk forwards with a ripple gait, sideways with a tripod gait. The robot could squat, it could stand, and it could turn on the spot. There are videos on my website, but it's such a short talk that I had to skip over some of these. And another kind of walking machine. Imagine a 6-legged walking machine. This time, encoders on the joints of the body enabled me, well, let's see what the machine looked like. This is part of the robot, or half of the robot. This robot is 5 meters in diameter. 5 meters in diameter. There. 1, 2, 3, 4, 5 in diameter. And it uses pneumatic rubber muscles, but these are much larger pneumatic rubber muscles that are over 1 meter in length. And antagonistically bundling these muscles, you could generate flexion and extension and function quite anatomically like our muscles contract and extend. And this sort of indicates how this works. If I lift one leg up, 3 robot legs lift and swing forward. So by stepping up and down on the spot, you can get the robot to walk, to turn, and there are sensors in the chassis which detect which direction the artist is facing, and the robot walks in that direction. So this was completed at Nottingham Trent University and was performed in London in 2006. And a smaller robot, this is called the walking head. And the idea with this robot was to try to make an actual virtual system. So the mechanical movements of the legs modulate the facial behaviour of the kind of human head. And the ultrasound sensor detects when someone's in the gallery, and when the robot senses that someone's there, the robot stands, selects from its library of possible movements, and then does a little performance for about a minute, minute and a half. It's a very noisy robot. Goes to sleep and waits for the next person to come along.
This video is over.
You probably know about this robot. It's the smaller brother of the big dog. So it's a little dog, and what's very seductive about this is the mammalian gait. It's seductively lifelike, even though we know it's a robot. It even has a handle, but it's still seductively lifelike in its movements. That's one of the approaches with robotics now, is biomimicry, studying insects and animals, and then sort of, in a sense, mimicking them, or translating those natural gaits into a robot. And this one actually also learns how to best traverse some rugged terrain. So this is a really more sophisticated robot, and also like the big dog, it can maintain its balance. And then another little robot, which is called Rex, and this one has a combination of wheels and legs, which they call WEGs, right? And so what it means is that it can move very fast on a flat surface, but it can also clamber over obstacles, and also these legs are sort of springy. So this robot can do very athletic feats of locomotion.
Come back, just got my license back. I got this feeling in my veins. The train is coming off the track. Alas, but lies, the devil needs a rocket, 'cause we ain't no love riding. And now I'm getting mad. I'm down to pass you out while you were speaking out. I got the gun on the gun so you can dump me on the run. Your mom don't know that you were missing. She can see the parts of you that I've been missing. Screaming out, never gonna quit. Ain't nothing wrong with it. Just have to live forever.
So being able to engineer robots that can move fast, jump high, have springiness in their locomotion is obviously an advantage. And I'll have to cut this video short, but it's available online, of course. You can just Google Rex and get the full video. And then another friend of mine, a roboticist in Dallas, Texas, David Hansen, created this humanoid head, which is called Diego. And 32 micromotors generate all of these facial behaviors. The robot can also speak phoneme sounds, so it has lip movements that can speak phoneme sounds, and it also has small cameras in its eyes to enable it to engage with a person that's talking to it. So it'll speak to you, it'll engage your gaze, obviously a much more seductive, interactive agent. Of course, it generates a somewhat uncanny feel to it, right? And you guys probably know about the uncanny valley, that as you try to engineer a robot that's more and more human-like, it becomes more and more creepy. Yeah. Now, is this a technical problem or a philosophical problem? It seems to me it's more of just a state-of-the-art problem that technologically, as robots, function more efficiently, more subtly, have more lifelike appearances, then I think they'll be convincingly human-like. And as I said before in the other talk, that it's not only creepy robots that we have to worry about. There's lots of creepy people in the world. So it's not only robots that malfunction, it's not only robots that perform strangely sometimes, but if you're not very socially adept, if you have a stammer, if you are aggressive, if you are antisocial in those ways, of course, you're also going to be somewhat creepy. So that's sort of an overview of the sorts of problems in robotics, which for me are really about how to generate aliveness and how to evoke agency. Because if a robot performs in a sophisticated way, if a robot can adapt and can perform appropriately in particular situations, then we can call that robot intelligent or somewhat intelligent. That robot will appear to have some kind of agency and autonomy. So what vocabulary of behaviour generates aliveness, whether it's an insect-like robot or whether it's a human-like robot, and what evokes a sense of intelligence and agency. And once we start building robots that exhibit those qualities, then they'll be much better to interact with. Okay, so I've been told to keep it down to 15 minutes and we've gone over that. Are there any questions about any of the projects? Or I had to do it at pretty much full speed to get through all this stuff. And I do have some additional slides which I haven't shown. But any questions about the projects or the performances? The other comment quickly to make is that in that performance, where I was controlling an extended arm, my left arm was automated, computer controlled with muscle stimulation. So in a way, this arm was machine-like, and this extended arm, which was a kind of a prosthesis, was in a way being humanised, and it was a kind of a split body experience. Left side, voltage in, involuntary movement, right side, voltage out, controlling an extended arm. Yes, sorry.
Which is your current project you're working on at the moment?
Well, several projects. We are incorporating 3D printing now, more and more. I mean, the ambidextrous arm has 3D printed components, but those components were pinned together, but we're now designing a whole hand with articulated joints where you could 3D print it in one go overnight, take it out of the 3D printer, stick a motor on it, and away it goes. Also, one of our students is working on an orthosis, a kind of exoskeleton for a paralysed hand. So then someone with a paralysed hand could be programmed to perform useful functions like wrist rotation, grasp and release functions. So again, those can be 3D printed all in one go. And we have a 16 micron resolution 3D printer at Curtin University, so it's possible to have very fine tolerances and to print very precise mechanisms, especially when you're dealing with mechanisms that have to be worn by a hand. They have to be fairly delicate, fairly precise. So that's one of the projects. So 3D printing is the way to go. And in fact, you've probably read research where they're developing the 3D printing of flat robots that when you apply electric current to them, the electroactive polymers in the seams fold the robot, so you can program how it folds up, and then it crawls away. So you can now laminate flexible circuitry with electroactive polymer film and produce a robot that walks effectively. They haven't completely 3D printed something like that, but they 3D printed similar sorts of things, and they've also developed the other laminated robots that I've talked about. Yes?
Do the robots carry all their computational power on them, or is that done off the robot?
Okay. Well, the interesting thing about the insect-like robots, right, is that effectively these are just dumb robots in the sense that there's really no meaningful computational power or processing done on them, right? Partly because they're designed with some basic sensors or with no sensors. For example, Rex, right? Even if Rex has no sensors at all, it has the locomotion possibilities. In other words, it has the musculature and the chassis to negotiate any kind of rough terrain or smooth surface. So in other words, its seeming complexity of behaviour is only an expression of the complexity of the world that it performs in.
So does it use a lot of computational power to calculate where to step, or is that quite simple?
No, that's just simple. I mean, basically, like for example, the simple WEGS robot, not this one, but the simpler one, has one motor only, and basically it has no sensors. It just basically, churns along and clampers over anything in its way. And it's like an ant. An ant doesn't have a big brain, but it does seemingly complex individual and collaborative tasks. Now, why is that? Why does an ant seem so kind of interesting or intelligent? Or why is it producing complex behaviour? Because it has to function in a complex world. It's expressing the contour of the environment that it's performing in. So you don't need robots to be smart in the sense of having to do a lot of crunching and processing. Otherwise, they'd take a step and they'd have to calculate all sorts of real-world scenarios before they took the next step. But there's an understanding that that doesn't happen in real life. We might have big brains, but insects don't. Insects manage, better than us a lot of the time. So, yeah.
I've got a question on the insect robot. You mentioned it's got the ability to learn from the environment. And what if the second time, when you go past the same environment, but the terrain has changed slightly? Is it going to use the knowledge learned from the previous one, or is it going to treat it as a new environment?
Yeah, look, I can't answer that properly because those other examples are shown are not mine, but I wanted to show you some interesting new research or recent research. So, if you Google those robots, I'm sure you'll be able to find some more specific technical information and how the sort of learning process occurs. But again, it doesn't have to be a complicated situation. Sometimes you can construct the architecture of the robot to be robust enough that it can basically kind of, muddle through and effectively without necessarily having to sort of think intelligently to do it.
Thanks.
Sorry, I can't respond.
Sure. I have a
Yes.
philosophical question. In this exhibition where you have your control,
Yes.
let's say you hit someone, that somebody is passing by, the computer goes in. Would you be illegally liable? You didn't do it. I mean, is it use your body?
Yeah, there's actually a pathological condition called the alien arm, and this is when your arm suddenly begins to act pathologically. You lose control of it. In fact, there was a famous case of a man who had this pathologic arm condition, and his arm kept trying to choke him. No, seriously, this was kind of a serious situation. But I mentioned an example in the other talk where I would love to be able to see with the eyes of someone, say, in New York, hear with the ears of someone in London, while someone in Tokyo is remotely accessing my arm and performing a task with it, and I could maybe collaborate with my own agency, So that would create a very interesting philosophical and physiological dilemma, because your sensory experience wouldn't be determined by the boundary of your skin, nor the local space that you inhabit. You would experience sensory information from different places, disconnected from each other, with other agents, multiple agents, affecting the movements of your own body. So I think we've got to stop.
That's okay, but if anyone has any questions, they can always, you're going to be around for a bit longer, Professor?
Not much longer because I've been given the lift here. I'm at Curtin University, so if anyone wants to get in touch, it's just simply Stelarc at Curtin. Okay, thank you. Thank you so much.
Thank you. Actually, very interesting. It's excellent that the students get exposed to these ideas. And I throw that to the second question.
Sorry about cutting you off.
No.
School reps are about to
Absolutely. No, another point.